Welcome to PICnMix, July 2021. In this month's article, we look at connecting our PIC18F development board to an IoT sensor, an environmental monitor. We use the board to monitor the device's solar panel output voltage and the charge status on a small lithium battery, so we can determine whether during the course of the year there's sufficient sunlight under all conditions to keep the sensor operational and the battery charged. So the way in which we've set up the board is we're using an op-amp to buffer the two voltage inputs here, which we're simulating using the two potentiometers on our board. We're buffering it before placing it into the ADC inputs, and we're using channel 0 and channel 5 as those are two available pins on our board. We have the board hooked up to power and a PIC-Kit 4, and a USB cable from the UART to USB converter is connected to our PC, so we can look to see whether we are successfully decoding the voltage levels, converting them correctly, and sending them out of the device. So we went through this in detail in the article, but as GUIs are very difficult to describe how to configure in text, so a video will almost certainly be easier to follow. So we start by running up MPLAB-X. We're using version 5.45, which as of this date is the latest version. So let's go ahead and create our first project. We'll go File, New Project. At this point we're asked what type of project we're building. Well, we're building a microchip embedded application, so we can click Next. And now we're prompted to enter the processor that's on our board. So it's a PIC18F47K42. And we can also select what debugging tool we're going to use. So we've got it plugged in at the moment, so let's go ahead and connect to our PIC-Kit 4, click Next. And now we can choose our compiler toolchain. We're going to use the latest version that we've installed. Now we can give a name to the project or the project files. We'll actually start by choosing a project location. We don't know why there's a location and a folder specified here. We don't adjust this. This will update automatically. So let's give it a directory name of solar test. And we'll give this project name, well, what is it that we're making? We're making a monitor, so we'll call it a monitor. You can place the file in any directory you wish and give it a name as you wish. Let's click Finished. And now that activity is complete. We have our project files created, but at this stage there are no source files. If we click here, nothing happens. If we look in the files list, we see only debug directories and a make file. No project files have been created. So at this stage we could go ahead and create our main.c manually, but we're going to use the Microchip Code Composer Tool. So we'll go ahead and click on that. And the first thing that happens is it asks us to choose a directory in which to save the configuration file for MCC. Well, it's going to, at the moment it's defaulting to our project directory, so that's fine for us. So let's just save it. And now in the middle of the screen here we can see the GUI for setting up the peripherals, and we can see them over here. So the project resources are the default resources that have been added to the project. So we see a pin module for configuring the default state of the pins. And then down here in device resources, this is a long list of assisted driver modules for developing code for the various peripherals and higher level functions such as file system and SD card that we can add easily to our project. So we're going to start with the Adc driver. Let's click on the diamond here beside the Adc peripheral and click on the green plus sign. And now the easy setup page for that module has appeared. So we can scroll down here and see the various settings that are available. The first thing that we need to do is to select the pins that we're going to be using. So we come down here to the module analog to digital converter, come across on the analog input lines, and we're going to select port A0 and port A5 because those are the two pins that we've chosen. And you can see that these have gone green and the lock item is closed to indicate that those pins are now locked for use to the ADC. So let's go ahead and generate some code. So this isn't building the project, this is generating the source files based on the settings that we've made in the various resources down here. And in the output dialog down here, you can see it's created a main.c for us and a number of driver files. There's the analog to digital converter, a pin manager driver, and a few other files as well. And we can now go and click on the Files tab and go that those driver files have been deposited in MCC generated files. Let's go and have a look. So if we open the source file for the Adc driver, we'll see a number of routines. Adc initialize, pretty clear what that's doing. That's the basic one-time initialization of the Adc module. And now here are a number of functions. There's no documentation here, but that's held in the header file. So if we scroll down again, and if we come down to the start conversion routine, we actually see that in the header comments, there's even a snippet of code here to show you how to use it. And this is actually very clear, and that's exactly what we want to do. That's the code that we want to run inside our application. Let's have a look at the main.c file to see what's been created for us there. So here's a function called system analyze, and if we navigate to that and have a look at it, we'll find that it calls the various peripheral initialization functions. So no great surprise there. Back in our main.c file, the main function itself is a list of initialization code. If we're going to use interrupts, which we will at some point later on, these are the two calls that they recommend that you make to enable and disable interrupts globally. And then they've written a little, or generated a little while loop here, and politely remind us that that's where our application code goes. So what we're going to do, if I go back to that header file, is we're going to implement this code within that while loop. We're going to do it twice, once for the solar panel voltage detection and once for the battery voltage detection. So if we come back here, I can type that in, but actually I can also be lazy because I've saved a copy of what I've written there. So let's come in and replace this with our code. So come down here and we can see those two blocks of code, very similar to what was in the header file description. The main difference being this last line of code, which converts the code that comes from the analog to digital converter to an actual voltage value in a floating point register. And then to actually get that information out of the board over the serial port, we're doing a printf here, and this is just going to run continuously with no delays, but that's okay because we're at this stage we're only really testing the we're only testing that the drivers are functional. So you notice here there's an error that it can't resolve printf. That's okay because I haven't included the header file yet for that. So let's go hash include stdio.h, save that, and that's it. For the purposes of this month's article, that's the code that we need to run. Unfortunately, this code won't run, and that's for two reasons. The first reason is that we haven't set a clock, an oscillator configuration setting, or rather the default clock configuration setting that is used by MCC is incorrect for our board design. MCC defaults to an expectation of an external crystal being fitted. We're not using an external crystal for our high frequency oscillator, we're using the internal one, so we're going to have to change that. And then the second reason why it won't work is that by default, and in fact actually by standard convention, the default implementation of printf does not actually push the characters from the string that it's generated anywhere. Its final lowest level call is to a function called putcha, which by convention is never implemented. It's left for the engineers to do that. So we're going to have to write a UART driver and fill in putcha. But once again, MCC comes to our aid, and if we go back to resource management and scroll down the peripherals, we will find a UART. So let's open that up. There are two UARTs available on this chip. Let's add the first UART again by clicking on the green plus. The UART1 dialog opens. So we're going to default to 9600 is okay, but this system is quite capable of running much faster than that. So we'll go to a higher baud rate, so we'll get faster output. The transmitter is already enabled. The receiver is enabled by default. We're not using the receiver, but we'll leave the code in there because it may come handy later on. Final change we're going to do here is to click on redirect stdio, standard input and output, to the UART, and clicking that is what causes MCC to fill in the putcha function. So let's go back to our first problem, which is the selection of the clock source. So I'll click on the system module, and here we are. We can see that the oscillator selection is assuming an external clock. We're not going to do that. We're going to use the high frequency internal oscillator. We now get a chance to specify at what speed that runs. We could go up to 64 megahertz, but I'm quite happy running at 16 megahertz. It will reduce the current consumption of the processor slightly. And then finally, so that you see with that settings, by default we get a system clock of 4 megahertz, but I'm going to bring that up to 16 megahertz by not having a clock divider. So great, so now we have a 16 megahertz clock, and we have the internal oscillator selected. So let's go and click generate again and generate the source files, and that's quite quick, and it's done. And what you can see here is that some of these files have been created. So here we go, there are some new files, but some files have been modified. So you see this auto merge, and indeed in some cases it's recognized that we have manually edited a file. MCC is quite intelligent in that way. It does understand about making changes to files without upsetting changes made by the user. If there's a conflict, so if it's trying to change a configuration setting to a value and we've already changed it to a different value manually, it will spot that and it will prompt for you to decide what you want to do. When you generate code, there is a notifications tab which lets you know if there are any conflicts in the configuration, and there's a hint here that the selected TAD, which is the time period for the acquisition on the analog to digital converter, is set too low, and that's happened because we set a fairly fast oscillator speed compared to what we had before. So that's fine. The ADC is quite configurable. We can go and change that. So let's click up here on the ADC, and again we can now see that clearly. It's telling us that with an ADC clock source of the main system clock divided by 2, its own internal timer is going to be too fast. Now, if you're sampling high speed or frequently changing analog signals, you'll want to calculate these acquisition times carefully so that you can have an acquisition time as fast as possible. Our solar panel voltage and battery voltage are changing very, very slowly, so we can be quite crude in our choice of clock settings, and I'm going to be quite generous. I'll come down here and I'm just choosing that at random, 50, dividing the oscillator by 50, and I'm going to specify a count of 1,000 here, which means that our acquisition time, how long it takes to sample the input signal, is 62 microseconds. That's perfectly fine. So we can click generate again. That's done. Look back on the notifications. No more hints. There's some informationals, but they're just informationals. So that's it in theory. There is one more thing. We've implemented a UART driver, but we haven't told the UART driver what pins we want to use, which would mean again that it's probably made an assumption. So we come back to the pin manager grid view and we scroll down until we find the UART. Now we want to specify a pin for the receiver, which is going to be port B3 on our board, and for the transmitter we're using port B2. Now we're using the port B pins here, and for those of you familiar with using pretty much any PIC, some pins on port B are often set to analog mode by default. So let's go to the pin module and look at our pins and see how they're configured. And sure enough, we can, as we come along here for the transmit and receive pins, we see that RB2 is currently set as an analog input, so we can unclick that, and MCC will now generate the code to switch from analog to digital. Right, let's click generate for hopefully the final time. And now, having done that, we can now build the code and run it, and we'll run it in the debugger. So if I click on the debug main project, that will cause the code to be compiled, as we could see there. There's a few warnings that certain modules haven't been called. That's fine. Click OK to that message, and apparently it's running. So let's open a terminal program, and I'm going to load that. We are on COM port 3 on our UART USB driver. And there we go. We have data. And if I were to twiddle those variable resistors, those values would change. So having done that, and assuming that you've gone through and debugged it thoroughly and you're happy with it, you can now program the board for independent operation, and that's this button over here. So let's click Make and Program. Click OK. And that's it. We're done. The code is now running. So I hope that that helped clarify the tutorial in the article, and I look forward to September issue, where we'll actually wire up the SD media card and the Wi-Fi interface, and put this in a box out in the sun with the device we're testing. Thank you. Goodbye.